every second somewhere in the cosmos, a galaxy crosses an invisible line and vanishes from our future forever. Light from over 2 trillion galaxies races toward Earth right now, but most of that light will never arrive. What brought you here tonight? Curiosity, insomnia, or just the algorithm? Tonight, we're exploring the universe's edge, and trust me, it's stranger than you think. If this cosmic paradox intrigues you, stay a while. A soft, like a quiet, subscribe, or even just your presence is welcome here. Let's begin. Every second somewhere in the cosmos, 20,000 galaxies cross an invisible line and vanish from your future forever. Light from over 2 trillion galaxies races toward Earth right now, but most of that light will never arrive. You stand inside a sphere stretching 62 billion light years in every direction, surrounded by an edge you can see forming in real time. Beyond that boundary lies infinity itself, endless and unknowable. Something impossible is happening right in front of you. The universe stretches forever in every direction, endless and without boundaries, yet you stand at the center of a sphere with edges you can measure precisely. Both statements are true. Both seem to contradict each other. This is the single most mind-bending paradox in cosmology, where infinity itself comes with limits. Think about this carefully. If you ask whether the cosmos has an edge, the answer is no. Space continues outward, without walls, without borders, without any kind of cosmic fence marking where reality ends. Galaxies exist beyond galaxies, structures beyond structures, extending into distances so vast that numbers become meaningless. The universe, confirmed through countless observations, is likely infinite in extent. But here comes the twist that changes everything. You cannot see all of it. You cannot reach all of it. You cannot even receive light from all of it. Despite living in an infinite cosmos, you are trapped inside a bubble. This bubble has measurable boundaries, real limits, and those limits are closing in on you right now. The edge isn't made of matter or energy. Nothing physical blocks your view. Instead, the boundary emerges from something far stranger. Time itself creates your prison. Light travels at exactly one speed through empty space, roughly 186,000 miles per second. Nothing moves faster. This cosmic speed limit has been the same since the universe began, roughly 13.8 billion years ago. Now combine these two facts, and you hit a wall. Light from distant regions has been racing toward Earth since the beginning of time, but it hasn't arrived yet. Some light will reach us tomorrow. Some will arrive in 1 billion years, but vast stretches of space sit so far away that their light will never complete the journey. That unreachable distance defines your edge. Scientists call this boundary the cosmic horizon, and it surrounds you in all directions. Everything inside this sphere represents the observable universe, the only region you can possibly detect or interact with. Everything beyond remains forever hidden, separated not by distance alone, but by the structure of space-time itself. You could build a spacecraft capable of traveling at light speed, point it toward that horizon, and accelerate for eternity. You would never reach it. The boundary would move away faster than you could approach. This gets stranger still. Your horizon is not the same as someone else's horizon. An observer on a planet in the Andromeda Galaxy sees a different sphere centered on their location. Parts of their observable universe overlap with yours, but vast regions they can see remain invisible to you. Every point in space has its own cosmic horizon, its own bubble, its own edge. Infinity contains countless edges, each one real, each one unique. We live in a universe that is both boundless and bounded, eternal and limited, infinite and trapped. Inside your body are atoms that were once part of stars at the rim of this sphere. But understanding your prison requires understanding the lock that seals it. Light moves at exactly one speed through empty space, about 186,000 miles every second. Nothing travels faster. This represents the ultimate cosmic speed limit. No exception, no loophole, no way around it. This speed limit has remained constant since the universe began, roughly 13.8 billion years ago. Every photon that has ever existed has obeyed this rule. Every photon that will ever exist must obey it too. Now, combine this absolute limit with the age of the universe, and something remarkable happens. You hit a wall, an invisible barrier that defines what you can possibly see. Light from distant regions has been racing toward Earth since the beginning of time, but it hasn't arrived yet. Some of that ancient light will reach us tomorrow, having traveled for billions of years through expanding space. Some will arrive in a billion years, still making its way across the cosmos. But vast stretches of space sit so far away that their light will never complete the journey. Not because the light stops, not because something blocks it, but because the universe simply hasn't existed long enough for those photons to cross the distance. That unreachable distance defines your boundary. Scientists call this edge the cosmic horizon. It surrounds you in all directions like an invisible sphere. Everything inside represents the observable universe, the only region you can possibly detect, measure, or interact with. Everything beyond remains forever hidden, separated not just by distance, but by the fundamental structure of space-time itself. This boundary is absolute. No technology can pierce it. No telescope can see past it. No signal can cross it. The laws of physics themselves create this wall. You could build a spacecraft capable of traveling at light speed, the fastest anything can possibly move. Point it toward that horizon and accelerate. Travel for 1 billion years, for 1 trillion years, for eternity itself. You would never reach it. The boundary would move away faster than you could approach. This sounds impossible. How can something recede faster than light speed when nothing moves faster than light? The answer reveals something profound about cosmic expansion, but we'll get to that. For now, understand this: the horizon exists. It's real, it's measurable, and it defines the ultimate limit of what you can ever observe. Here comes something even stranger. Your horizon is not the same as someone else's horizon. An observer on a planet in the Andromeda Galaxy, 2 million light years away, sees a different sphere centered on their location. Parts of their observable universe overlap with yours. You both see the same local galaxy cluster. You both detect the same cosmic microwave background radiation. But vast regions they can see remain invisible to you forever. Galaxies that sit within their horizon lie beyond yours. Structures they can measure will never appear in your telescopes. Their window into infinity shows different content than yours. Every point in space has its own cosmic horizon, its own bubble of observability, its own edge. Move 1 light year to the left, and your sphere shifts with you. New regions enter your horizon, while others slip beyond it. Every observer experiences this same phenomenon. An alien civilization 3 billion light years away sees their own sphere, their own horizon, their own observable universe. Some of the galaxies they can detect exist beyond your reach, invisible to you forever. Meanwhile, you can see galaxies that remain eternally hidden from them. The cosmos reveals itself differently to every observer, granting each one a unique window into infinity. Picture yourself standing in an enormous dark warehouse with a single flashlight. The beam illuminates a circle around you, creating a boundary between what you can see and what remains in darkness. Walk forward and the circle moves. The lit area never changes shape or size, but different parts of the warehouse come into view while others fade behind you. Your cosmic horizon works exactly this way, except the flashlight is time itself, and the warehouse is infinite. This creates a staggering realization about the true nature of cosmic observation. You are the exact center of the observable universe. Stand anywhere on Earth, anywhere in the galaxy, anywhere in the cosmos, and the same rule applies. You occupy the middle of a sphere that extends equally in all directions. Move one step to the left, and your sphere moves with you. Travel 1,000,000 light years, and nothing changes. The bubble follows you perfectly, always centered, always the same size. This isn't an illusion or a trick of perspective. This is fundamental cosmic geometry. Picture yourself standing in an enormous dark warehouse with a single flashlight. The beam illuminates a circle around you, creating a boundary between what you can see and what remains in darkness. Walk forward, and the circle moves. The lit area never changes shape or size, but different parts of the warehouse come into view while others fade behind you. Your cosmic horizon works exactly this way, except the flashlight is time itself, and the warehouse is infinite. Every observer in the universe experiences this same phenomenon. An alien civilization 3 billion light years away sees their own sphere, their own horizon, their own observable universe. Some of the galaxies they can detect exist beyond your reach, invisible to you forever. Meanwhile, you can see galaxies that remain eternally hidden from them. The cosmos reveals itself differently to every observer, granting each one a unique window into infinity. An observer in Andromeda sees roughly 2 trillion galaxies just like you, but their catalog differs from yours. Galaxies at the edge of their sphere lie beyond your horizon. Galaxies at the edge of your sphere lie beyond theirs. The overlap is substantial. You both see the Milky Way Andromeda, the local galaxy cluster. You both detect the cosmic microwave background. You both observe the same laws of physics operating across space. But the edges differ. The boundaries shift. Each observer occupies their own center, surrounded by their own walls. This creates something profound. No single viewpoint captures everything. No observer sits in a privileged position with access to more of reality than anyone else. The universe treats every location identically. Every point becomes a center. Every center defines its own sphere. You might think this makes you special. It doesn't. It makes everyone special, which means no one is more special than anyone else. This is the heart of the paradox. The universe has no center because every point is a center. The universe has no edge because every observer sees their own edge. Your observable universe follows you like a shadow. Move through space, and it moves with you. Wait billions of years, and it grows, revealing regions whose ancient light finally completes its journey, but it never reveals everything. The boundary always exists. The horizon always limits you. Every conscious being that has ever existed or will ever exist experiences this same cosmic isolation, each one trapped in their own bubble, each one seeing a unique slice of infinity, each one convinced they occupy the middle of everything. Because they do. You are the center of the observable universe, and so is everyone else. But the size of your bubble reveals something even more staggering about cosmic reality. No observer can see the entire universe. No location offers a complete view. Even if you could somehow survey every galaxy in your observable region, catalog every star map, every structure, you would still have examined only a tiny fraction of what exists. The full universe extends far beyond what any single observer can detect. Infinity ensures that everyone sees merely a sample, a cosmic preview, never the whole show. But your observable universe is not just large. The sphere surrounding you measures roughly 92 billion light-years across. That distance contains approximately 2 trillion galaxies, each holding hundreds of billions of stars. The numbers become incomprehensible quickly. 2 trillion galaxies, each one a vast island of stars, each star potentially hosting planets, each planet potentially harboring complexity. The scale staggers the mind. Count one galaxy per second, and you would need over 60,000 years to count them all. Yet this entire region, this vast cosmic domain, represents only a minuscule portion of total existence. If the universe is truly infinite, then your observable sphere is infinitely smaller than the whole, 0% of infinity. Let that sink in. Everything you can see, everything humanity has ever observed, everything our telescopes can ever detect, all of it represents 0% of what exists. The observable universe is to the full universe as a single atom is to nothing. The comparison fails. No finite number, no matter how large, makes a dent in infinity. Your bubble contains everything you can ever see, measure, or interact with. Every photon that strikes your eye or your telescope comes from within this sphere. Every scientific discovery, every astronomical observation, every piece of data about the cosmos originates from inside these boundaries. You are cosmically isolated, separated from the rest of infinity by unreachable limits. Think about what this means. Somewhere beyond your horizon, countless galaxies exist right now. They formed billions of years ago. They evolved through cosmic time. Stars ignited, burned, and died. Planets coalesced. Perhaps life emerged. Perhaps civilizations arose. Perhaps beings looked up at their night sky and wondered about their place in the cosmos. All of this happened. All of this continues happening, but you will never see it. No light from those regions will ever reach you. No information can cross the barrier. Those galaxies exist in the same universe as you, but they might as well exist in a separate reality. The observable universe represents everything accessible to you. Everything outside might as well not exist from your perspective. You cannot detect it. You cannot measure it. You cannot influence it. You cannot even confirm it exists, except through mathematical reasoning and cosmological models. It's like being given an infinite library, but only receiving a library card for one small room. The books in that room contain extraordinary knowledge. You could spend eternity reading them, but infinite rooms stretch beyond your access. infinite books remain forever closed to you. Your sphere contains 2 trillion galaxies. The full universe, if infinite, contains infinitely more. If your eyelids are growing heavy, let them close. The image of this 92 billion light-year sphere will follow you into sleep. But there's something else you need to know about cosmic distance. Something that changes everything. Light lies to you constantly about distance. Look at a galaxy 13 billion light years away. You see light that left 13 billion years ago. Simple math suggests that galaxy sat 13 billion light years from Earth when it released those photons. Wrong. The galaxy was actually much closer when the light began its journey. By the time those photons reach your telescope, that same galaxy now sits far beyond 13 billion light years. The light traveled through expanding space, and space itself betrayed the measurement. This deception reveals something profound about cosmic distance. When astronomers report distances to far objects, they often use light travel time. They measure how long light spent crossing space. A galaxy whose light took 10 billion years to arrive gets labeled as 10 billion light years away. But that number only tells you when the light left, not where the galaxy sits now. Space expanded during the journey. The galaxy drifted farther away while its light approached you. The current distance exceeds the light travel distance by enormous amounts. Consider the most distant galaxies visible today. Their light has been traveling for over 13 billion years, almost the entire age of the universe. Simple calculation suggests they sit roughly 13 billion light years away. Reality tells a different story. Those galaxies currently sit more than 46 billion light years from Earth. The expansion of space during the light's journey stretched the distance by more than 3 times. The galaxies moved while their light was in transit. Now, imagine trying to reach one of those galaxies. You build a spacecraft capable of traveling at light speed. You point it toward a galaxy whose light took 12 billion years to reach Earth. You might think the journey would take 12 billion years. You would be catastrophically wrong. That galaxy has been receding the entire time its light traveled toward you. The current distance exceeds 30 billion light years. Even moving at light speed, you could never catch it. The space between you and that galaxy expands faster than you can close the gap. Distance becomes slippery in an expanding universe. 2 galaxies can sit far enough apart that space between them expands faster than light travels. They drift apart at speeds exceeding the cosmic speed limit. Yet neither galaxy moves through space faster than light. They remain stationary in their local space. The space itself stretches, carrying them apart. The expansion of the universe does not obey the same rules as motion through space. This distinction is crucial. Special relativity limits how fast objects can move through space-time. Nothing can accelerate to light speed. Nothing can outrun a photon. But the expansion of space has no such restriction. Space can grow as fast as conditions allow. Distant galaxies, carried along by this expansion, can recede from each other at any speed whatsoever. This creates regions you can see but never reach. Galaxies beyond a certain distance, currently about 16 billion light years away, are crossing an invisible threshold. Light leaving them today will never arrive at Earth. The space between us and them expands too quickly. Those galaxies can still send signals to us from their past, but their present and future remain forever disconnected from ours. We can watch their history unfold, study their properties, measure their ancient light, but we cannot send them information. We cannot visit them. We cannot interact with them in any way. They are observationally present, but causally disconnected, visible ghosts beyond the point of contact. The universe splits into regions, separated not by distance, but by reachability, and this division reveals the two most important boundaries in the universe. Understanding these two boundaries requires understanding how space itself behaves. Space itself is growing larger every second. Forget the image of galaxies flying through empty void like bullets through air. That picture deceives you completely. Galaxies mostly sit still. The space between them expands, creating new distance where none existed before. Picture a loaf of bread dough with raisins mixed throughout. As the dough rises, the raisins move apart, but each raisin stays motionless relative to the dough around it. The dough itself grows, carrying the raisins along. The universe behaves like that dough, except the dough is space-time itself. This expansion has no center and no edge. Every point in space expands equally. An observer in any galaxy would see all other galaxies receding, creating the illusion they occupy the center of expansion. But no true center exists. The universe expands everywhere simultaneously, stretching the fabric of space-time uniformly in all directions. Space does not expand into anything. There is no container outside. The universe is all there is. Now measure this expansion, and something unexpected emerges. Nearby, galaxies recede slowly. Distant galaxies recede faster. Double the distance, and you double the recession speed. A galaxy 1 million light-years away might drift from us at 14 miles per second. A galaxy 2 million light-years away drifts at 28 miles per second. This relationship holds throughout the observable universe. The farther something sits, the faster it recedes. Push this pattern to its limit. At some distance, galaxies recede at exactly the speed of light. That distance currently measures roughly 14 billion light-years. Beyond that boundary, galaxies recede even faster. Some race away at twice light speed, some at 10 times. The most distant observable galaxies recede at approximately 3 times the speed of light. They violate no physical law because they do not move through space. Space itself carries them. Think about what this means. Right now, while you read this line, millions of galaxies are receding from you faster than light speed. Let that sink in. The cosmic speed limit still holds. Nothing can move through space faster than light. But space itself has no speed limit. It can stretch as fast as conditions allow. This distinction changes everything. When physicists say nothing moves faster than light, they mean nothing can move through space-time faster than light. A rocket cannot accelerate to light speed. A particle cannot outrun a photon. All motion through space obeys this absolute restriction. But the expansion of space involves something different. Space-time itself grows larger, and that growth has a speed limit. The fabric of reality can stretch at any rate whatsoever. Distant galaxies carried along by this expansion can recede from each other at any speed, not because they move through space, but because the space between them grows. The raisins in the bread dough do not move through the dough. The dough expands, carrying the raisins apart. The raisins remain stationary in their local dough, yet they separate at speeds determined by how much dough sits between them. Galaxies work exactly this way. A galaxy 1 billion light-years away recedes at a certain speed. A galaxy 10 billion light-years away recedes 10 times faster. Not because it moves faster through space, but because 10 times more space sits between us and it. And all that space expands simultaneously. Add up all the tiny expansions across vast distance, and you get enormous recession speeds. Speeds that exceed light. Speeds that would be impossible for anything moving through space, but perfectly normal for space itself expanding. This creates a profound realization about cosmic motion. Galaxies do not fly away from you. You're not at the center of some cosmic explosion. The Big Bang did not happen at a specific location that everything is flying away from. Instead, space grows, everywhere at once. Every cubic meter of space slowly becomes slightly larger. The growth seems tiny locally, but accumulated across cosmic distances, and it dominates everything. Space expands uniformly, but the effect accumulates with distance. Nearby regions show minimal expansion over human timescales. The space between Earth and the Sun barely changes. The space between the Sun and nearby stars grows but slowly. But the space between galaxies spans millions of light years. The expansion across those distances adds up, creating measurable recession speeds. The space between galaxy clusters spans hundreds of millions of light years. The expansion becomes dramatic. At the largest scales, expansion dominates. Galaxies in distant clusters race away from each other at speeds that would shatter every law of physics if they represented motion through space. But they do not represent motion through space. They represent the growth of space itself. Understanding this distinction unlocks the deepest mysteries of cosmic observation. It explains why you can see galaxies that recede faster than light. It reveals how light from the early universe reaches you despite traveling through expanding space. It defines the ultimate boundaries of what you can ever observe or influence. The expansion rate determines everything. Astronomers call this rate the Hubble constant. Currently, it measures about 14 miles per second per million light years. That means for every million light years of distance, recession speed increases by 14 miles per second. Travel 1 million light years from Earth, and galaxies there recede at 14 miles per second. Travel 2 million light years, and they recede at 28 miles per second. Travel 1 billion light years, and they recede at 14,000 miles per second. This relationship remains constant throughout space. Every observer measures the same expansion rate. Every location shows the same pattern. Recession speed increases linearly with distance until you reach the critical distance where recession equals light speed, currently about 14 billion light years away. This marks the Hubble distance, a crucial boundary in cosmic structure. Beyond the Hubble distance, recession exceeds light speed. Space expands faster than light can cross it. This creates regions you can see but never reach. Galaxies whose light reaches you, but whose present moment remains forever disconnected from yours. Two boundaries emerge from this expansion. Both shape what you can observe. Both define your cosmic prison. Both separate possible from impossible in ways that challenge every intuition. The first boundary lies in the past, the second in the future. Understanding both requires understanding something strange about how light behaves in expanding space. This creates bizarre consequences. Light from those super distant galaxies travels toward Earth at light speed, the fastest anything can possibly move. But the galaxies themselves race away faster than light. The photons make forward progress toward us, but they fight against the current of expanding space. Imagine swimming upstream in a current stronger than you can swim. You move forward through the water, but the water carries you backward faster. You make negative progress toward the shore. Light from distant galaxies experiences exactly this. Consider a photon from a galaxy receding at twice light speed. The photon travels toward us at light speed, but space expansion carries it backward at twice light speed. The net result: the photon actually moves away from us at light speed. The light loses ground despite traveling at maximum velocity. But here comes the strange part. Early in cosmic history, the expansion rate was slower. Back then, even though that galaxy receded faster than light, its light could make forward progress. The photons gradually closed the distance, eventually entering regions where expansion had slowed enough for them to reach us. We can see galaxies that always receded faster than light. Their light reaches us anyway, by starting the journey when expansion was slower and gradually entering regions where they could make progress. The observable universe contains countless galaxies that never at any point in their history receded slower than light relative to us. Yet we see them clearly. This seems impossible. How can light from a galaxy receding faster than light ever reach you? The answer lies in how expansion changes over time. In the early universe, space expanded rapidly, but the expansion was decelerating. Gravity from all the matter in the universe pulled back on the expansion, slowing it gradually. A photon leaving a very distant galaxy fought against fierce expansion. It made little progress. It might even move away from Earth initially, but the expansion was slowing. Each passing million years, the expansion weakened slightly. The photon persisted. It continued traveling at light speed, and the expansion it fought against grew gradually weaker. Eventually, the photon entered regions of space where local expansion no longer exceeded light speed. The photon began making net progress toward Earth. Over billions of years, that photon crossed unimaginable distances, always traveling at light speed, always fighting expansion, but gradually winning the battle as expansion weakened. Finally, after more than 13 billion years of travel, that photon reaches your telescope, stretched into infrared or microwave wavelengths by the expansion, but carrying information about a galaxy from the early universe. You see that galaxy, despite it always receding faster than light. The photon's journey succeeded because expansion slowed over time, but the situation has changed. About 5 billion years ago, cosmic expansion began accelerating. Something called dark energy started dominating the universe. This mysterious component does not dilute as space expands. Unlike matter and radiation, which spread thinner as volume increases, dark energy maintains constant density. Create new space, and you create new dark energy. This accelerates the expansion. More space means more dark energy, which means faster expansion, which means even more space. A runaway feedback loop. This acceleration changes everything about cosmic boundaries. In a decelerating universe, every galaxy eventually becomes observable. If you wait long enough, light from any galaxy, no matter how distant, will reach you. The weakening expansion eventually allows all photons to make progress. but in an accelerating universe that changes. If expansion accelerates, some galaxies will remain forever beyond reach. Light leaving them today will never arrive. Not in a billion years. Not in a trillion. Never. The acceleration creates a permanent boundary, an event horizon for the universe itself. Photons from galaxies beyond this horizon fight a losing battle. They travel toward Earth at light speed, but space expansion carries them backward faster. And unlike in the past, the expansion no longer weakens. It strengthens. The photon loses ground. Today, tomorrow, forever. No matter how long it travels, it can never reach you. Space expansion ensures it drifts farther away despite racing towards you. Think about what this means for observation. Right now, you can see galaxies whose light has traveled over 13 billion years. That light began its journey in the early universe, when space expansion was slower. The photons fought against expansion, but gradually won, eventually reaching Earth. But those same galaxies crossed a threshold billions of years ago. Light they emit today will never reach Earth. The accelerating expansion prevents it. The photons drift away despite traveling at light speed toward us. You see those galaxies past, but their present and future remain forever hidden. You watch a delayed broadcast of their history, but their current state lies beyond reach, beyond observation, beyond knowledge. Every day, thousands of galaxies cross this threshold. They slip beyond the point where communication becomes possible. You can still see their old light for billions of years, but new light from them will never arrive. When the last ancient photons from those galaxies reach Earth, no replacements follow. The galaxies fade from view, red-shifting into invisibility, stretching by expansion until detecting them requires impossible sensitivity. This creates a strange form of cosmic blindness. Imagine watching a distant spacecraft through a telescope. The ship crosses a threshold where signals can no longer escape. You continue seeing it because old light keeps arriving, but that light shows increasingly outdated information. You see the ship as it was 1 minute ago, then 5 minutes ago, then an hour ago. The image redshifts, dims, and freezes at the moment of crossing. You never see what happens after. The ship appears locked at the boundary forever, fading into darkness. Galaxies beyond the event horizon behave exactly this way. You see them as they were when light escaped their local region, before space expansion trapped subsequent photons. Their image freezes, redshifts, and vanishes. The observable universe loses galaxies permanently. Even while remaining infinite in extent, the visible cosmos shrinks, even as total cosmic space continues growing. The rules governing cosmic vision challenge simple intuition, but they also define the ultimate boundaries of observation, two boundaries that emerge from how space itself expands. The first boundary marks how far light has traveled since the beginning. The second marks how far light emitted now could ever travel in the future. Both boundaries move, but they move in opposite directions. Understanding why requires understanding something profound about time itself. The sphere surrounding you measures 92 billion light-years across. That boundary marks the farthest distance from which light could have possibly reached Earth since the universe began. Anything beyond that distance remains invisible. Not because instruments lack power, not because technology falls short, but because not enough time has passed for light to complete the journey. The universe is 13.8 billion years old. Light traveling at constant speed for that entire duration covers a certain distance. Simple math suggests light should reach about 13.8 billion light years in 13.8 billion years. But space expanded while the light traveled, stretching the journey, placing the source much farther away than 13.8 billion light years. Current calculations place your horizon at 46 billion light years in every direction. Double that distance and you get the diameter, 92 billion light years from edge to edge. This sphere contains everything you can possibly observe. Every photon ever detected by human instruments originated from inside this boundary. Every star, every galaxy, every quasar, every cosmic structure, visible to telescopes, sits within this cosmic prison. Beyond the wall lies infinity itself, forever inaccessible. But the wall appears differently, depending on what you look for. The oldest light you can detect is not visible light at all. It comes as microwaves, ancient radiation stretched by expansion into long wavelengths. This radiation fills the entire sky, coming from all directions equally. It represents light released when the universe was just 380,000 years old, about 46 billion light years away from us today. That shell of ancient light marks the practical edge of observation. Beyond that shell, the universe was opaque. You cannot see farther because light could not travel freely through the early cosmos. Matter was too hot, too dense, too ionized. Photons scattered constantly off free electrons, unable to travel in straight lines. Picture a thick fog where every water droplet deflects light. You cannot see through it no matter how powerful your eyes. The early universe was like that fog, except instead of water droplets, free electrons filled all space. Photons bounced endlessly, making no forward progress. Only after the universe cooled enough for atoms to form did light finally break free. Electrons combined with protons. Neutral atoms formed. Free electrons vanished. Suddenly, space became transparent. Light could travel unimpeded across cosmic distances. That moment of liberation created the shell of radiation you detect today. Anything that happened before that moment remains hidden behind an impenetrable curtain. The first 380,000 years of cosmic history are fundamentally invisible to light-based telescopes. You might imagine peering farther back with powerful enough instruments, but no telescope can pierce the plasma curtain. It represents an absolute barrier to electromagnetic observation. This creates a nested set of boundaries. The theoretical limit at 46 billion light years represents how far light could travel in principle. The practical limit sits at roughly the same distance, but represents the moment the universe became transparent. Between you and that wall lie all 2 trillion galaxies of the observable universe, arranged in an intricate cosmic web of filaments and voids. Beyond the wall lies the unobservable universe, potentially infinite in extent. Think about what this means. The observable universe contains 2 trillion galaxies. Each galaxy holds hundreds of billions of stars. Each star potentially hosts planets. The numbers become staggering. Count 1 galaxy per second, and you would need over 60,000 years to finish. Yet this entire region represents only what light has had time to reach you. The full universe extends beyond. How far beyond? If space is infinite, then infinitely far beyond. Your observable sphere is to the full universe as a single atom is to all the atoms in existence. Actually worse, a single atom to infinity. 0% of everything. The wall is real. The wall is absolute. The wall cannot be crossed by any technology or method you can imagine. You cannot see past it. You cannot receive signals from beyond it. You cannot even confirm what lies beyond it, except through mathematical reasoning and cosmological models. It's like standing in thick fog. You see 100 meters around you, but the world does not stop there. It continues beyond your vision, endless terrain stretching in all directions. But the fog blocks your view. The fog creates your wall, for the universe time creates the fog. The finite age of the cosmos ensures light from distant regions has not arrived yet. Some will arrive tomorrow, some in 1 billion years. Some will never arrive at all. This brings us to the second boundary, one that sits much closer, one that defines not what you can see, but what you can reach. But even within your sphere, not everything remains reachable. A second boundary exists much closer than the first, currently sitting about 16 billion light years away. This boundary separates regions you can see from regions you can influence. Galaxies beyond this closer boundary are crossing a threshold. Even if you sent a light speed signal toward them right now, that signal would never arrive. Space expands too quickly. The message would drift farther from its target forever, making progress through space but losing ground to expansion. You can see these galaxies, but you can never contact them. They exist in your observable universe, but outside your reachable universe, you can watch their past unfold, study their properties, measure their light, but you cannot send them information. You cannot visit them. You cannot interact with them in any way. They are observationally present, but causally disconnected, visible ghosts beyond the point of contact. This second boundary shrinks with every passing moment. More galaxies cross it constantly, slipping beyond reach forever. Each day, about 20,000 galaxies cross the event horizon. They vanish from your reachable future. You can still see them because their old light continues arriving, but new light from them will never complete the journey. The galaxies at the edge of the observable universe recede at three times the speed of light. Let that sink in for a moment. The speed of light represents the ultimate cosmic speed limit. Nothing can travel faster, yet galaxies routinely exceed this limit by factors of 2, 3, or more. They violate no physical laws. They break no rules. The cosmos allows this because the rule about light speed applies to motion through space, not to the expansion of space itself. Special relativity sets the speed limit for objects moving through space-time. A rocket cannot accelerate to light speed. A particle cannot outrace photons. All motion through space obeys this absolute restriction. But the expansion of the universe involves something different. Space itself grows larger, and that growth has no speed limit. The fabric of space-time can stretch as fast as conditions allow. Distant galaxies carried along by this expansion can recede from each other at any speed whatsoever. Think about the bread dough again. The raisins do not move through the dough. The dough expands, carrying the raisins apart. Each raisin sits motionless in its local dough. Yet raisins on opposite sides of the loaf separate at speeds determined by how much dough sits between them. Expand the dough fast enough, and distant raisins separate faster than light could cross the dough. The raisins violate no speed limit. They do not move. The dough moves them. Galaxies work exactly this way. Picture two galaxies separated by enormous distance. The space between them expands everywhere, simultaneously. Near Earth, a small amount of new space appears every second. Near the distant galaxy, another small amount appears. All along the path connecting them, space expands at the same rate. Add up all these small expansions across millions or billions of light years, and the total distance grows faster than light can travel. Neither galaxy moves through space faster than light, but the space carrying them expands without limit. This creates a strange consequence for light traveling between them. Photons from ultra-distant galaxies fight against expansion. They race toward Earth at maximum speed, but space carries them backward faster than they advance forward. Early in the universe's history, when expansion was slower, these photons could make progress. They gradually closed the distance, despite swimming upstream against expansion. Eventually, they entered regions where local expansion had slowed enough for them to reach us. We see them now as ancient, red-shifted light from near the cosmic horizon. But photons emitted from those same galaxies today will never arrive. The current expansion rate exceeds the rate when that ancient light was emitted. Modern photons face a stronger current. They cannot make progress against it. They will drift away from Earth forever, despite traveling at light speed toward us. The galaxy that emitted them recedes faster than its own light can approach us. This defines the event horizon, the boundary separating galaxies we can still communicate with from galaxies forever beyond reach. Every second, about 20,000 galaxies cross this threshold. They slip beyond the event horizon, entering the unreachable realm. You can still see them because their old light continues arriving, but light they emit today, tomorrow, or any time in the future will never complete the journey. You are watching the last visible moments of these galaxies, frozen in time as they cross into cosmic isolation. Over billions of years, they will fade from view completely as their final photons arrive and no new ones follow. Think about what this means for cosmic observation. Imagine watching a distant spacecraft through a telescope. The ship crosses a threshold where signals can no longer escape. You continue seeing it because old light keeps arriving, but that light shows increasingly outdated information. You watch the ship as it was 1 minute ago, then 5 minutes ago, then an hour ago. The image redshifts, dims, and freezes at the moment of crossing. You never see what happens after. The ship appears locked at the boundary forever, fading into darkness. Galaxies beyond the event horizon behave exactly this way. You see them as they were when light escaped their local region, before space expansion trapped subsequent photons. Their images freeze, redshift, and vanish. The observable universe loses galaxies permanently, even while remaining infinite in extent. Your visible cosmos shrinks even as total cosmic space continues growing. The event horizon currently sits about 16 billion light-years away. That makes it much closer than the observable horizon at 46 billion light-years. You can see galaxies far beyond the event horizon because their past light made the journey when conditions were different. But those distant galaxies are already unreachable. They crossed the event horizon long ago. Their current state, their present condition, their modern evolution remain forever hidden from view. This split between observation and interaction defines your cosmic reality. The universe you can see extends much farther than the universe you can reach. You are watching a delayed broadcast of cosmic history, seeing galaxies as they were billions of years ago. But their present moment lies beyond contact, beyond communication, beyond influence. The universe found a loophole in physics law. Space itself does not need to follow the speed limit, and this loophole seals your fate. It guarantees increasing isolation. It ensures that more of the cosmos slips beyond reach with every passing moment. The event horizon contracts. The reachable universe shrinks. Your cosmic neighborhood empties. This is not science fiction. This is established cosmology, confirmed by observation, verified by measurement, written into the equations that govern cosmic expansion. Every day, you lose access to 20,000 galaxies. Every year, you lose access to 7 million. Every century, 700 million galaxies slip beyond reach. The future is lonelier than the past, and nothing can prevent it. Picture two galaxies separated by enormous distance. The space between them expands everywhere simultaneously. Near Earth, a small amount of new space appears every second. Near the distant galaxy, another small amount appears. All along the path connecting them, space expands at the same rate. Add up all these small expansions across millions or billions of light years, and the total distance grows faster than light can travel. Neither galaxy moves through space faster than light, but the space carrying them expands without limit. This creates a strange consequence for light traveling between them. Photons from ultra-distant galaxies fight against expansion. They race toward Earth at maximum speed, but space carries them backward, faster than they advance forward. Think of a swimmer in a river. The swimmer moves forward through the water at their maximum speed. But if the current flows backward faster than they can swim, they make negative progress toward shore. They move forward through the water, yet drift farther from their destination with every stroke. The swimmer expends maximum effort, pushes through the water with everything they have. But the current overwhelms their progress. They lose ground despite swimming as fast as physically possible. Light from distant galaxies experiences exactly this. Photons travel toward us at light speed, the fastest anything can move. Yet space expansion carries them away faster than they approach. The photons race forward at maximum cosmic velocity, but the river of expanding space flows backward even faster. Net result, negative progress. The light moves away from us despite traveling toward us. Early in the universe's history, when expansion was slower, these photons could make progress. The current was gentler then. The photons gradually closed the distance. Despite swimming upstream against expansion, they fought against a weaker flow, making slow but steady progress toward Earth. Eventually, they entered regions where local expansion had slowed enough for them to reach us. The current weakened as they traveled, until finally they escaped the strongest flow and completed their journey. We see them now as ancient red-shifted light from near the cosmic horizon. Here comes something remarkable. The universe contains countless galaxies that never, at any point in their history, receded slower than light relative to us. These galaxies always moved away faster than light, from the moment they formed until today. Not once did they slow below light speed relative to Earth. Yet we can see them clearly. Their light reached us anyway, by starting the journey when conditions were different, by gradually entering regions where they could make progress. The photons launched into a strong current. But that current weakened over time as the universe's expansion rate changed. The photons swam through an easing flow, eventually entering regions where they could overcome the expansion and reach us. This defies simple intuition. Galaxies receding faster than light should be invisible. Their light should never arrive. Yet the observable universe contains them, visible despite always exceeding light speed. The rules governing cosmic visibility operate on principles stranger than straightforward logic suggests. But here comes the critical change that seals the future. Photons emitted from those same galaxies today will never arrive. The current has strengthened. The expansion rate now exceeds what it was when that ancient light was emitted. Modern photons face a stronger flow. They cannot make progress against it. A photon leaving that galaxy right now travels toward Earth at light speed, maximum velocity, yet space carries it backward at twice light speed. The photon moves forward through space, but space itself drags it backward faster. Net result: the photon drifts farther from Earth despite racing toward us. It will drift away from Earth forever despite traveling at light speed toward us. The galaxy that emitted it recedes faster than its own light can approach us. This defines the event horizon, the boundary separating galaxies we can still communicate with from galaxies forever beyond reach. Every second, about 20,000 galaxies cross this threshold. They slip beyond the event horizon, entering the unreachable realm. You can still see them because their old light continues arriving. Photons emitted before the crossing, when conditions were different, complete their journey. They bring images of the galaxy as it was, information from its past, messages sent before the door closed. But light they emit today, tomorrow, or any time in the future will never complete the journey. Those photons launch into a current too strong to overcome. They will never reach Earth, never deliver their message, never update us about the galaxy's present condition. You are watching the last visible moments of these galaxies, frozen in time as they cross into cosmic isolation. The stream of arriving photons shows progressively older images. You see the galaxy as it was 1 million years before crossing, then 10 million years before, then 100 million years before. The timeline runs backward as the final photons arrive, each one launched earlier than the last, each one carrying increasingly outdated information. The most recent events fade first, then earlier moments, then ancient history, like watching a film in reverse. The galaxy appears to age backward, its present slips away, its near past follows, until only its distant past remains visible, and then eventually, even that fades. Over billions of years, they will fade from view completely as their final photons arrive and no new ones follow. The galaxy's image will redshift into invisibility, stretch into undetectable wavelengths, dim beyond any possible observation threshold, and then nothing. The galaxy disappears from your observable universe, not because it ceased to exist, but because all communication has been severed. The event horizon currently sits about 16 billion light-years away. That makes it much closer than the observable horizon at 46 billion light-years. You can see galaxies far beyond the event horizon because their past light made the journey when conditions were different. Their ancient photons escaped before the current became too strong. Those photons carry images of galaxies as they were billions of years ago. young, actively forming stars full of cosmic youth. But those distant galaxies are already unreachable. They crossed the event horizon long ago. Sometime in the deep past, those galaxies drifted beyond the point where communication remains possible. The door closed, the connection severed, the isolation became permanent. Their current state remains forever hidden from view, their present condition unknowable, their modern evolution invisible. What happened to them after crossing you, we'll never know. Did they merge with other galaxies, form new generations of stars quiet into cosmic old age, suffer catastrophic collisions? The answers exist, but they remain forever beyond observation. This split between observation and interaction defines your cosmic reality. The universe you can see extends much farther than the universe you can reach. The observable universe stretches to 46 billion light years. The reachable universe extends only to 16 billion. A vast domain exists where you can receive messages but cannot send them, where you can watch but cannot touch, where you can observe but cannot influence. These galaxies are observationally present but causally disconnected, visible ghosts beyond the point of contact. You see their past. You study their properties from billions of years ago. You measure their ancient light, but you cannot send them information, cannot visit them, cannot interact with them in any way. The separation is absolute and permanent. Think about what this means at a deeper level. Right now, civilizations might exist on planets orbiting stars in those unreachable galaxies, beings who look up at their night sky, who study their cosmos with instruments and curiosity, who see our Milky Way as a faint smudge of ancient light in their telescopes. We can see each other, but we can never contact each other, not with radio signals traveling at light speed, not with laser beams cutting through the void, not with any form of communication physics allows. The space between us expands too quickly. Any message we send will drift away from them forever, making progress through local space, but losing ground to expansion. Any message they send drifts away from us the same way. We are cosmically isolated despite being mutually visible, separated by expansion rather than distance alone. Two civilizations, both gazing across the universe, both seeing each other's ancient past, both forever unable to make contact, to share knowledge, to communicate in any way. This represents a profound form of loneliness, built into the structure of space-time itself, guaranteed by the mathematics of cosmic expansion, unavoidable and permanent. No technology can overcome it. No clever trick can circumvent it. The isolation is written into the fundamental laws governing reality. But the isolation grows worse with time, because these two boundaries move in opposite directions. The particle horizon expands. Every second light from more distant regions completes its journey and enters your observable sphere. The past reveals itself gradually. New galaxies come into view. Ancient light arrives for the first time. Light that has been traveling for billions of years finally completes its journey. Your window into history grows larger. The observable universe increases in content as well as size. Meanwhile, the event horizon contracts. Every second more galaxies cross the threshold where communication becomes impossible. The future closes off. The reachable universe shrinks. Your window into the present narrows. Galaxies that were barely contactable yesterday slip beyond reach today. The domain of possible interaction decreases continuously. One boundary opens while the other closes. You gain access to the past while losing access to the future. You see more ancient galaxies while watching present galaxies slip beyond reach. The universe reveals its history while concealing its destiny. Eventually, billions of years from now, the two horizons will converge. The particle horizon will reach its maximum size, while the event horizon shrinks to a minimum. After that point, your observable universe stops growing. The window reaches its widest extent for viewing the past, but closes completely for influencing the future. No new galaxies will enter visibility. No remaining galaxies will stay reachable. The observable universe will contain a fixed inventory of objects, all from the past, none accessible in the present. This is the heart of cosmic isolation. Two boundaries, moving in opposite directions, one revealing history, the other sealing destiny, and you trapped between them, watching the universe disappear in real time. The two boundaries tell different stories about time. The particle horizon speaks of the past, of light that began its journey billions of years ago, of galaxies as they were in cosmic youth. The event horizon speaks of the future, of connections being severed, of isolation becoming permanent. Two edges to your cosmic sphere, one expanding, one contracting. These are the key to understanding the fate of the universe. Take a deep breath and imagine these two boundaries, one from the past, opening wider, one from the future, closing shut, both moving through cosmic space, both defining what you can know and what you can reach, both shaping your place in the infinite cosmos. 380,000 years after the universe began, something changed forever. Before that moment, the cosmos was a roaring furnace of naked particles. Electrons drifted free, unbound to atomic nuclei. Photons scattered constantly off these free electrons, bouncing from particle to particle like pinballs in a machine. Light could not travel in straight lines. The universe was opaque, a thick plasma fog impenetrable to electromagnetic radiation. You could not see through it, no more than you could see through a wall of solid metal. The early cosmos resembled the interior of a star, dense, hot, ionized. Every photon that tried to travel got intercepted immediately, scattered by a free electron, redirected in a random direction, only to scatter again within a tiny fraction of a second. Light existed, but it could not travel freely. It remained trapped in an endless dance of scattering and rescattering. Photons bounced endlessly between particles, never making progress, never escaping, locked in a cosmic prison of interactions. Temperature determined everything. When matter exceeds about 5,000 degrees, electrons tear free from atoms. The electromagnetic force binding them breaks down. The thermal energy becomes too great for atoms to stay together. Electrons and nuclei separate, creating a state of matter completely different from what we experience in everyday life. Protons and electrons drift separately, creating a plasma where charged particles swarm everywhere. This state of matter behaves nothing like the cool, transparent gas filling space today. In plasma, particles carry electric charge. They interact strongly with electromagnetic radiation. They create an environment hostile to light propagation. Light interacts strongly with free electrons. The photons and electrons exchange energy constantly. Every time a photon encounters a free electron, which happens almost instantly. In dense plasma, the photon scatters, changes direction, loses or gains energy, then immediately encounters another electron and scatters again. The photon makes no progress through space. It bounces randomly, like a drunk person trying to walk forward, but constantly being pushed in random directions. The average distance traveled before scattering becomes vanishingly small. Light cannot penetrate the plasma fog. This creates opacity. The universe becomes a thick fog to light. Photons cannot penetrate more than a tiny distance before scattering again. The mean free path the average distance light travels before interacting measures smaller than the width of an atom today. Lower the temperature below 5,000 degrees, and everything changes. Electrons recombine with nuclei. Atoms form for the first time in cosmic history. Hydrogen atoms appear as electrons bind to protons. Helium atoms form as electrons attach to helium nuclei. Free electrons disappear, locked inside stable atomic structures. Suddenly, light can travel unimpeded across cosmic distances. The fog lifts. The universe becomes transparent. Photons that previously scattered every fraction of a second can now travel billions of light years without interruption. The mean free path becomes effectively infinite. This transition happened across the entire universe almost simultaneously. As expansion cooled the cosmos, conditions reached the critical temperature everywhere at once. The universe had been expanding and cooling since the Big Bang. Temperature dropped uniformly across all of space. When it fell below the critical threshold, atoms formed everywhere within a relatively short period. Electrons combined with protons and helium nuclei. Within about 100,000 years, the universe transformed from opaque to transparent. The change swept across cosmic space, not like a wave moving through space, but rather as a transition occurring everywhere at the same moment as temperature dropped below the critical threshold. Think about fog lifting on a cold morning. As the sun warms the air, the fog gradually dissipates, first thinning, then developing gaps, then vanishing completely. The cosmic transition worked similarly, but across the entire universe, all at once, within a cosmologically brief period. All the light that had been trapped, scattered endlessly by free electrons, suddenly broke free. It streamed outward in every direction, no longer blocked by interactions, no longer scattered by free electrons, free to travel across the cosmos for the first time, carrying information about the conditions at that moment, the temperature of matter at recombination, the density of particles in different regions, the tiny fluctuations that would eventually become galaxies, the motion of gas clouds, the sound waves rippling through the early universe. All of this got encoded in the light released when atoms formed. That light has been traveling toward you ever since, stretched by expansion, red-shifted from visible light into microwaves, cooled from thousands of degrees to just above absolute zero. It fills the sky today as a faint glow called the cosmic microwave background. Every direction you look, you detect this ancient radiation. Point a radio telescope anywhere, away from the sun, away from planets, away from our galaxy, and you find this signal, always present, always with the same properties, coming from all directions equally. It represents light, released from a spherical shell surrounding you, currently sitting about 46 billion light years away. That shell marks the surface of last scattering, the moment when photons last interacted with matter before beginning their long journey to Earth, the instant when the universe became transparent and light escaped for the first time. This is the farthest thing you can see with light. Beyond it, the universe was opaque. Light could not travel freely. Photons remained trapped in the plasma, scattering endlessly without making progress. No telescope, no matter how powerful, can see past this barrier. You might imagine looking farther back with powerful enough instruments, building larger mirrors, gathering more photons, increasing sensitivity, developing new technologies, waiting centuries for better detectors. But no telescope can pierce the plasma curtain. It represents an absolute barrier to electromagnetic observation, not a technological limitation, not a temporary obstacle to be overcome with better instruments, but a fundamental limit built into the nature of the early universe. Before atoms formed, light could not travel. The plasma scattered every photon immediately. Therefore, light-based telescopes cannot see those earlier moments. No amount of technological advancement can overcome this. You cannot use light to see an era when light could not travel. Everything that happened before atoms formed remains hidden behind this wall of scattered light. The first 380,000 years of cosmic history are fundamentally invisible to light-based telescopes. That entire epoch exists beyond the reach of electromagnetic observation. You cannot see the moment of the Big Bang itself, cannot observe the first microseconds when the universe was hottest and densest, cannot watch directly as the fundamental forces separated, cannot witness the formation of the first atomic nuclei. All of this occurred before the plasma cleared. All of it remains hidden behind the wall. But the cosmic microwave background itself reveals extraordinary detail. Temperature variations across the sky show tiny fluctuations in density, the seeds of all future cosmic structure. These variations measure about 1 part in 100,000, incredibly small, nearly uniform, but not perfectly smooth. Regions slightly denser than average appear as hotspots, slightly hotter by millionths of a degree. These overdense regions contained more matter, stronger gravity. These tiny differences seem insignificant, but they determined the future of cosmic structure. Regions slightly less dense appear as cold spots, slightly cooler by millionths of a degree. Less matter, weaker gravity, destined to become the voids between galaxies. These variations would eventually collapse under gravity to form galaxies. Matter in the overdense regions pulled together over billions of years, first forming gas clouds, then collapsing into the first stars, assembling into proto-galaxies, growing through mergers, building the massive galaxies visible today. Regions slightly less dense became the voids between galaxy clusters. Matter drained out of these underdense areas, flowing toward the overdense regions like water finding the lowest point, leaving behind vast empty spaces, cosmic voids hundreds of millions of light years across. The entire large-scale structure of today's universe traces back to these microscopic fluctuations visible in the ancient light. Every galaxy, every cluster, every void originates from tiny density variations, present when the universe was 380,000 years old. The cosmic web of filaments and voids, the superclusters, the great walls of galaxies, all grew from these quantum seeds. Looking at the cosmic microwave background means looking at the oldest possible image of the universe. It represents baby pictures of the cosmos, taken when everything was simpler, smoother, more uniform, before gravity amplified small differences into dramatic structures, before stars ignited, before galaxies assembled, before the universe developed its current complexity. The universe, in its infancy, captured in ancient light. Since that moment, gravity has been working, amplifying the small variations into the magnificent complexity visible today, pulling matter together in overdense regions, allowing underdense regions to empty out. The universe started nearly uniform. Time and gravity transformed it into the structured cosmos we observe. But that ancient light also reveals something else crucial about cosmic geometry. The universe at that early time was already enormous, already expanding, already following the rules that govern it today, already billions of light years across, not a small compact region, but a vast cosmic expanse. The cosmic microwave background confirms several fundamental facts about cosmic structure. The universe had no center even then, no special location from which everything expanded, no cosmic origin point sitting somewhere in space. The radiation comes from all directions equally, shows no preferred direction, reveals no center to the expansion. Instead, expansion occurred everywhere simultaneously, just as it does today. Every point in space moved away from every other point. Space itself grew larger, carrying matter along with it. The cosmic microwave background confirms the universe was remarkably uniform, nearly the same temperature and density everywhere, with only tiny variations of 1 part in 100,000. This uniformity poses a puzzle cosmologists call the horizon problem. How did distant regions reach the same temperature when they had never been in contact, when light had not had time to travel between them? But scientists hope to see farther back using other signals. Gravitational waves and neutrinos can pass through the plasma that trapped light. These messengers interact much more weakly with matter than photons do. They could carry information from even earlier moments, potentially from the first second after the universe began, from instants after the Big Bang, when conditions were far too extreme for light to travel. Gravitational waves, ripples in space-time itself, pass through matter almost unimpeded. A gravitational wave from the early universe would travel straight through the plasma, unaffected by the electrons and nuclei that scattered light. These waves could bring information from the moment of cosmic birth, from the era of inflation, from the first tiny fraction of a second. Future detectors might pierce the plasma curtain using these alternative messengers. Gravitational wave observatories, sensitive enough to detect primordial signals, space-based interferometers, ground-based detectors, technology not yet imagined. These instruments could reveal what happened before the universe became transparent to light. But for now, the cosmic microwave background marks the limit of what you can see. It defines the practical edge of your observable universe, the oldest electromagnetic signal, the most ancient light, the ultimate barrier to optical observation. Every time you turn on a television and see white noise, 1% of that static is echo from the moment the universe first became transparent. Photons from the cosmic microwave background red-shifted into radio wavelengths striking the antenna. Ancient light from the edge of the observable universe mixed with electronic noise flickering across the screen. Ghost signals from cosmic dawn. The sky glows with invisible fire. Point any radio telescope at empty space, away from planets, stars, or galaxies, away from any obvious source of radiation, and you detect something unexpected. Not silence, not emptiness, but radiation, a faint signal, coming from everywhere at once. Not random noise, but a precise signal with exact properties. This radiation arrives from every direction simultaneously, forming a spherical shell around Earth. No matter which way you point your antenna, you find the same signal, same intensity, same spectrum, same temperature. It represents the oldest light in the universe, stretched by expansion into microwave wavelengths. Light that began its journey when the cosmos was just 380,000 years old. Ancient photons that have been traveling through expanding space for over 13 billion years. Cosmologists call it the cosmic microwave background, and it marks the edge of observational reality. This radiation began its journey 13.8 billion years ago. Well, almost 13.8 billion. The universe was 380,000 years old when this light was released, making the radiation 13.79962 billion years old. Not quite as old as the universe itself, but close, very close. That tiny difference matters because it reveals something crucial. The universe had already expanded significantly before light could travel freely. The cosmos was not infinitesimally small when atoms formed. It had already grown to enormous size through 380,000 years of expansion, already billions of light years across, already governed by the same expansion that continues today. The cosmic microwave background comes from a shell of space that was much closer to Earth when the light was emitted. Current distance to that shell measures about 46 billion light years. But when the radiation left, when atoms first formed and photons escaped, the entire observable universe was just 42 million light years across. Expansion has stretched everything by a factor of roughly 1100 since then. The light itself has stretched by the same amount. Photons that left as visible or ultraviolet light now arrive as microwaves with wavelengths about 1 millimeter long. What started as orange or blue light has been pulled to wavelengths 1,000 times longer, transformed from visible radiation into invisible microwaves. This stretching reveals the expansion history of the universe. The wavelength of light tells you exactly how much space has grown since the photon was emitted. Measure the redshift. Compare the observed wavelength to the original wavelength, and you calculate how much the universe expanded during the photon's journey. For the cosmic microwave background, that factor equals 1100. The universe today is 1100 times larger than when these photons were released. Every distance has grown by this factor. Every wavelength has stretched proportionally. Temperature tells the same story. When the cosmic microwave background was released, the universe blazed at about 5,400 degrees, hot enough to glow orange-red, hot enough to ionize atoms, hot enough that matter and radiation were tightly coupled through constant interactions. The entire cosmos filled with this thermal radiation. Every cubic centimeter of space held photons at this temperature. Today, that radiation measures just 2 2.7 degrees above absolute zero, 2.7 Kelvin on the absolute temperature scale, colder than the vacuum of space between stars, colder than anything naturally occurring on Earth, nearly at the lowest possible temperature physics allows. The cooling tracks expansion precisely. As space grows, radiation within it loses energy. The wavelengths stretch, the frequency decreases, and the temperature drops in perfect proportion to the expansion. Double the size of the universe, and you have the temperature of the radiation. Triple the size, and you reduce temperature to 1/3. The relationship follows exact mathematical laws derived from thermodynamics and relativity. Expansion acts like a cosmic refrigerator, not by removing heat to some external reservoir, but by stretching wavelengths, by diluting energy density, by spreading photons across ever larger volumes. The radiation cools because space itself grows larger, but temperature varies slightly across the sky. One direction might measure 2.726 degrees, while another direction measures 2.724 degrees. The differences seem tiny, measured in millionths of a degree, barely detectable even with sensitive instruments. But these tiny variations tell the story of cosmic structure formation. These tiny variations measured in millionths of a degree reveal the structure of the early universe. Hotter spots represent regions slightly denser than average, more matter concentrated in those areas, more atoms per cubic meter, slightly more gravitational pull. These overdense regions show up as warmer temperatures in the cosmic microwave background, not because they were actually hotter, but because photons climbing out of their slightly stronger gravitational wells gained a tiny bit of extra energy. Cooler spots show regions slightly less dense, less matter, fewer atoms per cubic meter, weaker gravity. These underdense regions appear as cooler temperatures in the ancient light. Photons from these regions had slightly less energy when they escaped. The variations measure about 1 part in 100,000. For every million photons at exactly average temperature, one differs by just 10 photons worth of energy. Incredibly uniform, nearly perfectly smooth, but not quite. Those tiny imperfections made all the difference. Gravity has been amplifying these variations for 13.8 billion years, transforming tiny temperature differences of millionths of a degree into the massive structures visible today. The overdense regions pulled in more matter, grew denser, pulled harder, accumulated even more matter, a runaway process driven by gravity. Eventually, these regions collapsed completely, forming the first gas clouds, then the first stars, then the first galaxies, building the cosmic web of filaments and clusters visible today. Every galaxy traces its origin to a tiny hot spot in the cosmic microwave background. The underdense regions did the opposite. Matter drained out of them, flowing toward the overdense areas. The regions grew emptier, eventually becoming the cosmic voids, vast spaces hundreds of millions of light years across, containing almost no galaxies. The cold spots in the microwave background mark where these voids would form. The cosmic microwave background also reveals the geometry of space itself. Hot and cold spots appear at specific angular sizes across the sky, measuring about 1 degree in diameter. This size depends critically on the curvature of space. The geometry of the universe determines how large features appear at cosmological distances. If the universe curved like a sphere, the spots would appear larger. Light would travel along curved paths, magnifying the apparent size. Like looking through a magnifying glass, features would seem bigger than in flat space. If space curved like a saddle, they would appear smaller. Light would travel along different curved paths, shrinking the apparent size. Features would seem smaller than in flat space. Observations show the spots match predictions for flat space almost perfectly. The universe appears to have exactly zero curvature, within measurement error of 0.4%. The best measurements scientists can make reveal no deviation from perfect flatness. Space follows Euclidean geometry. Parallel lines stay parallel forever. Triangles have angles summing to exactly 180 degrees. The Pythagorean theorem holds across cosmic distances. All the rules from high school geometry apply to the universe at large. This flatness reveals something extraordinary about cosmic density. For space to be flat, the universe must contain a precise amount of matter and energy, not approximately the right amount, not close enough, but exactly the right amount. This critical density equals about 6 hydrogen atoms per cubic meter on average. Count all the ordinary matter, all the dark matter, all the dark energy, add them together, divide by total volume, and you get this exact number, 6 atoms per cubic meter. Not 5, not 7, 6. Too much total density, and space curves inward, creating positive curvature. Like the surface of a sphere, the universe would be finite in volume, eventually collapsing back on itself. Too little total density, and space curves outward, creating negative curvature, like a saddle shape. The universe would expand forever, opening faster and faster. The measured density sits right at the critical value, balanced on a knife edge. Perfect flatness. This balance seems too perfect to be coincidental. Why should the universe have exactly the density needed for flat space? Why not slightly more or slightly less? Early in cosmic history, even tiny deviations from flatness would have grown rapidly. If the density was 1% too high initially, the universe would have recollapsed billions of years ago. If 1% too low, space would curve obviously today. Yet observations show near-perfect flatness within less than 1% of the critical value. After 13.8 billion years of expansion that should amplify any initial deviation. This suggests either remarkable cosmic coincidence or some underlying principle that forced the universe toward this special geometry. Most cosmologists favor the second option. Some mechanism must have driven space toward flatness. Cosmic inflation provides the leading explanation. A brief period of exponential expansion in the first fraction of a second stretched space so much that any initial curvature became undetectable, like inflating a balloon to enormous size. The surface appears flat to anyone sitting on it. The cosmic microwave background contains more information than astronomers have fully extracted. Future measurements will reveal smaller temperature variations, more detailed patterns, subtle features currently hidden in noise, hidden signals buried in the ancient light that require better instruments and longer observation times to detect. Each new detail refines understanding of cosmic history. Each improved measurement constrains theories about the early universe. Scientists study the cosmic microwave background with ever-increasing precision. looking for clues about inflation, about the nature of dark matter, about the properties of dark energy, about the physics governing the first moments of cosmic existence. They map the distribution of hot and cold spots with increasing detail, looking for subtle patterns that reveal the physics governing cosmic birth, testing theories about inflation, measuring parameters that determine cosmic fate. Every new satellite, every new telescope, every new analysis technique extracts more information from this ancient light. Each new observation adds pieces to the puzzle, but the fundamental limit remains fixed. You cannot see past this wall of light. The cosmic microwave background defines the edge of electromagnetic observation. Behind it lies the plasma era, forever hidden from direct view. Like looking at an old, faded photograph. You see the past, but not with perfect clarity. The colors have faded, details have blurred, and you cannot look deeper, cannot see what came before the photo was taken, cannot rewind time to view earlier moments. The cosmic microwave background is that photograph, the oldest possible image of the universe, faded by expansion, blurred by distance, but still carrying information from cosmic dawn. Your universe has two boundaries, and they tell different stories about time. The first boundary, the particle horizon, defines how far light could have traveled since the universe began. It represents the past, marking the boundary of everything whose light has had time to reach you, currently sitting about 46 billion light years away. This horizon expands constantly as the universe ages. Every second that passes, light from more distant regions completes its journey and enters your observable sphere. The particle horizon grows, revealing new cosmic territory. Galaxies that were always there but remained invisible become observable for the first time. Their ancient light finally arrives after billions of years of travel. The observable universe increases in size continuously, not because new galaxies come into existence, but because light from existing distant galaxies reaches us for the first time. The sphere of observability expands at roughly the speed of light, growing by about 1 light year in radius every year. The second boundary, the event horizon, defines something stranger. This boundary marks the farthest distance from which light emitted right now could ever reach you in the future. It represents a division between galaxies you can still communicate with and galaxies forever beyond reach, currently sitting about 16 billion light years away. The event horizon is much closer than the particle horizon, less than half the distance. This creates a vast domain where you can see galaxies but cannot contact them, cannot send them messages, cannot influence them in any way. They exist in your observable universe, but outside your reachable universe. But here comes the disturbing part. The event horizon does not expand. In a universe dominated by dark energy, it actually contracts. This boundary is not static, not fixed in place. It moves inward over time, shrinking the domain of possible communication, sealing off more of the cosmos with every passing moment. These two horizons move in opposite directions. As time passes, the particle horizon expands outward. You see light from more distant regions, light emitted long ago, ancient photons from cosmic dawn. The past reveals itself gradually. History becomes visible as light completes its long journey. Meanwhile, the event horizon contracts inward. Fewer galaxies remain contactable, with each passing moment, the future closes off. The domain of possible interaction shrinks. Galaxies that were barely reachable yesterday slip beyond reach today. One boundary opens while the other closes. You gain access to the past while losing access to the future. The universe reveals its history while concealing its destiny. Eventually, billions of years from now, the two horizons will converge. The particle horizon will reach its maximum size, no longer expanding, frozen at a fixed distance, determined by the acceleration of cosmic expansion. Meanwhile, the event horizon shrinks to a minimum, also frozen at a fixed distance. The two boundaries approach each other asymptotically. After that point, your observable universe stops growing. The window reaches its widest extent for viewing the past, but closes completely for influencing the future. No new galaxies enter visibility. The inventory of observable objects becomes fixed, frozen forever. Picture what this means for cosmic observation. Right now, you can see galaxies whose light has been traveling for over 13 billion years. These galaxies sit more than 30 billion light years away due to expansion. Their ancient light shows them as they were in the early universe, young and actively forming stars, blazing with the blue light of massive young stars, full of gas clouds collapsing into stellar nurseries. But those same galaxies crossed the event horizon long ago. Sometime in the deep past, perhaps billions of years ago, those galaxies drifted beyond the point where communication remains possible. Light they emit today will never reach Earth. The photons launch toward us at light speed, but space expansion carries them backward faster than they advance. They make negative progress, drifting farther from Earth, despite racing toward us at maximum speed. You are watching a delayed broadcast of their past, seeing them as they were when light could still escape their local region, but their present remains forever unknowable. What do those galaxies look like today? Have they merged with neighbors, formed new generations of stars, exhausted their gas supplies, and gone quiet? You will never know. The images you see show galaxies frozen at the moment. They crossed the event horizon. Their evolution beyond that point remains hidden. Their current state invisible. Their modern structure unknowable. Thousands of galaxies cross the event horizon every single day. They slip beyond the boundary where communication becomes impossible. About 20,000 galaxies per day drift across this threshold. 7 million per year. 700 million per century. The numbers accumulate relentlessly. The reachable universe empties at an accelerating rate. You can still see their old light for billions of years to come. Photons emitted before they crossed continue arriving, each one carrying information from before the crossing, images from when communication was still possible, messages sent before the door closed. But new light from them will never arrive. When those final ancient photons reach Earth, no replacements follow. The stream of information cuts off. The connection severs permanently. The galaxy disappears from your present. You see only its past, forever frozen, forever unchanging, like a photograph that never updates. These galaxies will gradually fade from view. Their images will redshift into invisibility, stretched by expansion until the wavelengths become undetectable, dimmed by distance until no telescope can gather enough photons. The galaxies do not cease to exist. They simply fade beyond the threshold of observation, becoming invisible ghosts, present but undetectable. This creates a bizarre form of cosmic blindness. Imagine watching a distant spacecraft through a telescope. The ship travels away from you, crossing a threshold where signals can no longer escape. You continue seeing it because old light keeps arriving, light that left the ship before it crossed the threshold. But that light shows increasingly outdated information. You watch the ship as it was 1 minute ago, then 5 minutes ago, then an hour ago. The timeline runs backward. Recent events fade first, then earlier moments, then ancient history. The image redshifts. Colors shift toward red, then infrared, then radio wavelengths. The ship dims, grows fainter, harder to detect. The image freezes at the moment of crossing. You never see what happens after. The ship appears locked at the boundary forever, fading into darkness, dimming asymptotically toward invisibility, but never quite disappearing, just becoming too faint to detect. Galaxies beyond the event horizon behave exactly this way. You see them as they were when light escaped their local region, before space expansion trapped subsequent photons, before the current became too strong for light to overcome. Their images freeze, redshift, and vanish. The observable universe loses galaxies permanently, even while remaining infinite in extent. Your visible cosmos shrinks even as total cosmic space continues growing. The observable universe contains fewer galaxies over time, not because galaxies are destroyed, but because they drift beyond observational reach, carried away by expansion faster than light can follow. You become increasingly isolated in an observable sphere that is expanding but emptying, growing larger in size but containing fewer objects. The paradox of cosmic expansion: more space, less content, growing emptiness. This represents the far future of observation. Billions of years ahead, astronomers will detect fewer galaxies than you can see today. Their observable universe will contain less variety, fewer examples of cosmic structure, reduced astronomical diversity. Some types of galaxies visible now will have faded completely. Entire classes of objects disappearing from the observable catalog. Future civilizations might develop cosmology with incomplete data, missing crucial examples of cosmic evolution that crossed the event horizon before their species emerged. They might never see certain types of galaxies, never observe certain stages of stellar evolution, never detect certain cosmic structures, all because those objects faded beyond reach before observers evolved to study them. Think about what they would miss. The most distant quasars, those brilliant beacons from cosmic dawn, will have faded into invisibility. The early universe will become unobservable. The first generation of galaxies gone. The cosmic microwave background will have redshifted into undetectable radio wavelengths. Evidence for the Big Bang will have vanished. These future observers might examine their night sky and see only their local cluster of galaxies, perhaps 50 galaxies bound together by mutual gravity. Beyond that darkness, empty space, extending infinitely, they might conclude they live in a static, eternal universe. One small island of matter surrounded by infinite void. They would be completely wrong. The universe beyond their horizon continues expanding, filled with countless galaxies they cannot see, teeming with structure they cannot detect, rich with complexity beyond their observational reach. But they would have no way to discover this truth. all evidence exists beyond their horizon. All contradicting data has redshifted into invisibility. Their science would be limited by cosmic expansion, by the contraction of the event horizon, by the inexorable march toward isolation, like moving to a new city, where every day an old friend blocks your number. The connections sever one by one. People you could once reach drift beyond contact. Communication becomes impossible. The network of relationships shrinks until only the closest bonds remain. Everyone else has disappeared beyond an uncrossable barrier. Your descendants, thousands of generations hence, will look at a night sky far poorer than what you see today. They will count fewer galaxies, observe less diversity, study less structure, not because they lack better telescopes, not because they lack curiosity or intelligence, but because the universe itself has hidden more of its contents, drawn the curtains, closed the windows, sealed off vast domains of space. The contraction of the event horizon guarantees increasing isolation. Dark energy seals off more of the universe with each passing moment. This is not speculation, not theoretical possibility, but established cosmology, confirmed by observation, written into the equations governing cosmic expansion. The universe you inhabit will become lonelier over time, inevitably, inexorably, without exception. But why does the event horizon contract while the particle horizon expands? The answer lies with dark energy. This mysterious component dominates the cosmic inventory, making up roughly 68% of all energy density in the universe, more than twice the contribution from all matter combined. Dark energy has a strange property unlike anything in everyday experience. Normal matter dilutes as space expands. Spread the same number of atoms across larger volume, and density decreases. Double the size of a container, and you have the density of gas inside. This follows basic physics. Conservation of mass. Atoms neither created nor destroyed, just spread thinner. Dark energy does not dilute. It maintains constant density. Create new space through expansion, and you create new dark energy to fill it. The total amount increases as volume increases. More space means more dark energy, which means faster expansion, which creates even more space. A runaway feedback loop. This accelerates expansion itself. Early in cosmic history, when matter dominated, expansion was slowing. Gravity pulled back against the expansion, decelerating the growth of space. The universe expanded, but at a decreasing rate. About 5 billion years ago, dark energy began dominating over matter. Expansion started accelerating, growing faster over time, the rate of growth increasing. This acceleration changes cosmic horizons dramatically. In a universe filled only with matter, the event horizon would sit infinitely far away. Every galaxy, no matter how distant, would eventually become reachable if you waited long enough. Light from anywhere could reach you, given a sufficient time. The entire universe would eventually become observable and reachable. But our universe contains dark energy, and dark energy changes everything. In an accelerating universe, the event horizon converges to a fixed distance. Currently, at about 16 billion light years, it will asymptotically approach 17.6 billion light years over cosmic time. This represents the maximum distance from which light emitted at any future moment can reach us. Galaxies beyond this ultimate horizon are forever beyond contact, no matter how long you wait, no matter what signals you send. The isolation is permanent and absolute. The two boundaries tell different stories about time. The particle horizon speaks of the past, of light that began its journey billions of years ago, of galaxies as they were in cosmic youth. It expands, revealing more history, more ancient light, more distant objects from long ago. The event horizon speaks of the future, of connections being severed, of isolation becoming permanent. It contracts, sealing off more present-day galaxies, cutting communication, guaranteeing loneliness. Two edges to your cosmic sphere, one expanding, one contracting. These are the key to understanding the fate of the universe, the destiny of observation, the future of cosmic knowledge. Take a deep breath and imagine these two boundaries, one from the past opening wider, revealing ancient galaxies, bringing light from cosmic dawn, the other from the future closing shut, sealing off present-day galaxies, cutting connections, creating isolation, both moving through cosmic space, both defining what you can know and what you can reach, both shaping your place in the infinite cosmos. Every minute light from about 20 million galaxies crosses an invisible threshold and begins losing its battle against space. These photons will never reach Earth. They launch toward us at maximum cosmic speed, racing through expanding space at light velocity, the fastest anything can possibly move. Yet they drift farther away with every second that passes. The expansion of the universe overwhelms their forward progress. They fight against a current stronger than their speed, swimming upstream against a flow they cannot overcome, making negative progress despite moving as fast as physics allows. Think of a runner on a treadmill. The runner sprints forward at top speed, legs pumping, muscles straining, maximum effort. But if the treadmill moves backward, faster than the runner moves forward, the runner loses ground, drifts toward the back of the belt, makes negative progress despite running as fast as humanly possible. Light from distant galaxies experiences exactly this. Photons race toward Earth at 300,000 kilometers per second, but space carries them backward at 600,000 kilometers per second. Net result, they move away from Earth at 300,000 kilometers per second. Despite traveling toward us at maximum speed, this defines your future horizon, the boundary beyond which the cosmos becomes unreachable. The event horizon currently measures about 16 billion light years away, but this distance will change, not randomly, not unpredictably, but according to exact mathematical laws governing cosmic expansion. In a universe filled only with matter, the event horizon would sit infinitely far away. Every galaxy, no matter how distant, would eventually become observable if you waited long enough. Patience would be rewarded with universal access. Light from anywhere could reach you given sufficient time. Even photons fighting against expansion would eventually win, because matter-dominated expansion decelerates, slows over time, eventually allowing light to catch up. But our universe does not contain only matter. Dark energy dominates the cosmic inventory, making up roughly 68% of all energy density, more than twice the contribution from ordinary and dark matter combined. This mysterious component determines cosmic fate, controls the expansion rate, seals the future. Dark energy has a strange property that violates everyday intuition. Normal stuff dilutes as space expands. Spread atoms across larger volume, and density decreases. Pour milk into a larger container, and concentration drops. Double the size, and you have the density. This follows basic conservation laws. The same amount of matter occupies more space. Therefore, density must decrease. Dark energy does not work this way. It maintains constant density as space expands. Create new space through expansion, and you simultaneously create new dark energy to fill it. The density stays exactly the same, always, everywhere, at all times. This violates intuition built from everyday experience. How can you create more of something without a source? Where does the new dark energy come from? The answer involves quantum field theory and vacuum energy. Empty space itself possesses energy. As you create more empty space through expansion, you automatically create more of this vacuum energy. Normal stuff spreads thinner when volume increases. Dark energy does not. The total amount of dark energy in the universe increases as expansion creates more volume. More space means more dark energy, which accelerates expansion, which creates even more space, in a runaway feedback loop that never stops. This acceleration changes cosmic horizons dramatically. In an accelerating universe, the event horizon converges to a fixed distance. Currently, at about 16 billion light-years, it will asymptotically approach 17.6 billion light-years over cosmic time. This represents the maximum distance from which light emitted at any future moment can reach us. Think about what this means. Draw a sphere 17.6 billion light-years in radius centered on Earth. Every galaxy currently inside this sphere can potentially send us messages. Their light emitted today has a fighting chance of reaching us eventually. The current might be strong, but not insurmountable. Every galaxy currently outside this sphere is forever beyond contact. No matter how long you wait, no matter what technology you develop, no matter how patient you remain, light they emit now will never arrive. The current is too strong, the expansion too fast, the gap unbridgeable. Galaxies beyond this ultimate horizon are forever beyond contact, cosmically isolated despite existing in the same universe, sharing the same space, following the same physics, yet separated by uncrossable expansion. Picture the implications stretching across deep time. Right now, you can see about 2 trillion galaxies. That represents the current inventory of the observable universe. 2 million galaxies, each containing hundreds of billions of stars. The numbers become incomprehensible. The scale defies human intuition. That number will decline, inevitably, inexorably, without exception. Over the next 100 billion years, galaxies will cross the event horizon and fade from view as their final photons arrive. Not quickly, not dramatically, but gradually, steadily, relentlessly. The observable universe will empty out like water draining from a bathtub, slowly at first, then faster still. The rate of loss accelerates over time. In the near future, relatively few galaxies cross the threshold each century. But as dark energy dominates more completely, as expansion accelerates further, the rate increases. More galaxies slip beyond reach each year, each decade, each millennium. Eventually, only galaxies bound to our local gravitational group will remain visible. Perhaps 50 galaxies total, maybe fewer. These galaxies orbit each other too closely for expansion to separate them. Gravity holds them together despite cosmic expansion. They will eventually merge over billions of years, colliding, combining, forming a single giant elliptical galaxy. everything else will have redshifted into invisibility, their light stretched into undetectable wavelengths by relentless expansion. The photons still exist, still travel through space, but their wavelengths have grown so long that no conceivable detector can measure them, stretched beyond radio waves, beyond anything technology could possibly detect. Future civilizations will inhabit a lonelier cosmos. Imagine astronomers 100 billion years from now, evolved on planets orbiting stars in our galaxy or nearby, perhaps descendants of humanity, perhaps entirely different species that evolved long after humans went extinct. They develop science, build telescopes, study their cosmos with instruments and curiosity. They look into the night sky and see almost nothing beyond their local cluster, perhaps 50 galaxies scattered across the heavens. No distant quasars, no galaxy clusters, no cosmic web, just their local group surrounded by darkness, empty space extending infinitely in all directions. The cosmic microwave background will have redshifted into radio waves, then into wavelengths too long to detect with any antenna. The ancient glow marking the edge of the observable universe will have faded beyond measurement, stretched by expansion until completely undetectable. Evidence for the Big Bang will have vanished. The smoking gun of cosmic expansion will have disappeared. The most important observational proof of modern cosmology will no longer exist, erased by the very expansion it once revealed. These future scientists might examine their observations carefully, measure galaxy motions, study stellar evolution, map the local cluster, and conclude something completely wrong. They might determine they live in a static eternal universe, one small island of matter surrounded by infinite empty space, a cosmos that has always existed, that will always exist unchanged, that contains nothing beyond what they can see. They would be completely wrong, catastrophically mistaken about the fundamental nature of reality. The universe beyond their horizon continues expanding, filled with countless galaxies they cannot see, teeming with stars they cannot detect, rich with structure completely beyond their observational reach. Trillions of galaxies exist out there, but every single one sits beyond the contracted event horizon, forever invisible, forever unknowable. But they would have no way to discover this truth. All evidence exists beyond their horizon. All contradicting data has redshifted into invisibility. Every clue pointing toward the true nature of the cosmos has faded beyond detection. They could develop sophisticated theories, build powerful instruments, conduct careful observations for thousands of years, and still miss the larger cosmic reality. Their observable universe tells an incomplete story, a profoundly misleading story. They see their local cluster and conclude it represents everything. They measure no expansion and conclude the universe is static. They find no evidence for the Big Bang and conclude the cosmos is eternal. Every conclusion would be wrong, but they would have no way to know, no data to contradict their theories, no observations to challenge their models. Cosmic expansion has hidden the truth, sealed the evidence beyond reach, guaranteed their ignorance. This raises an unsettling question about our own era. What if we are already in such a position? What if crucial evidence about cosmic structure exists beyond our current horizon, forever hidden? What if our observable universe is unrepresentative of the full cosmos? The universe we observe might not be typical. Patterns visible to us might be local accidents, not universal features, statistical flukes confined to our observable region. We assume our patch of space shows typical cosmic properties, representative samples, fair examples of universal structure. But we cannot verify this assumption, cannot check whether our region is normal or exceptional, cannot compare our observable universe to the unobservable regions beyond. The data lies forever beyond reach, hidden behind horizons we cannot cross. We assume uniformity, assume our local region resembles the whole, assume cosmic democracy, where every location sees roughly the same thing. But we cannot prove this, cannot test it observationally, cannot rule out the possibility that we occupy an unusual region. Infinity beyond our horizon remains unknowable, forever hidden, forever mysterious. We make assumptions about it based on what we can see, but those assumptions might be wrong, completely wrong, and we would have no way to discover our error. The contracting event horizon guarantees increasing isolation. Dark energy seals off more of the universe with each passing moment, not metaphorically, not approximately, but literally, physically. The reachable cosmos shrinks continuously. This is the saddest part of the story, the most melancholy aspect of cosmic reality. The universe becomes lonelier over time, inevitably. Without exception, future observers will see less, know less, understand less, not through any failure of intelligence or technology, but through the inexorable contraction of cosmic horizons. But this is also the part that shows we are living in a special time. Right now, in this cosmic moment, the universe reveals itself clearly. The cosmic microwave background remains detectable. 2 trillion galaxies lie within observational range. Evidence for the Big Bang persists. Cosmic expansion can be measured. The history of the universe can be reconstructed from observable data. We live in the golden age of cosmology, a brief window when the universe shows itself. Before us, the cosmos was too young, too hot, too simple to produce observers. After us, the universe will be too old, too expanded, too isolated for observers to see clearly. The age of observability spans perhaps 100 billion years, from when the universe cooled enough for stars to form until expansion carries all evidence beyond horizons. The total lifetime of the universe may extend for trillions of years or more. We occupy a tiny fraction of cosmic time, a special moment when observation remains possible, when evidence still exists within reach, when the cosmos can still be understood. Your descendants, thousands of generations hence, will look at a night sky far poorer than what you see today. They will see fewer galaxies, less structure, less diversity. The universe will have hidden more of its treasures, drawn more curtains, closed more windows, but you see the universe in its glory, while it still reveals itself, before the horizons contract too far, before the evidence fades completely. You live in the brief era when cosmic truth remains accessible. This is not just sad, it is also precious. It makes observation valuable. It makes understanding urgent. It makes your cosmic moment special in the vast sweep of time. But even within your observable sphere, something else defines the cosmic boundary. Space can curve in 3 possible ways, and only one allows infinity. Imagine walking forward on a perfectly flat surface forever. You never return to your starting point. You never encounter an edge. The surface extends infinitely in all directions. This represents flat geometry, where parallel lines stay parallel, and triangles always have angles summing to 180 degrees. Flat space follows the rules you learned in school, the geometry of Euclid that describes everyday experience. Draw a triangle on paper, and its angles sum to exactly 180 degrees. Measure the angles carefully. Use a protractor. Add them up. Perfect flatness gives perfect results. Now picture walking on the surface of a sphere. Travel in any direction, and you eventually return to where you started. The surface has no edge, no boundary, yet it contains finite area. Walk far enough, and you complete a circuit. Return to your origin, despite never encountering a wall or barrier. Parallel lines drawn on a sphere eventually meet. Start 2 lines parallel at the equator. Extend them toward the pole. They converge, intersect, no longer parallel. The curvature of space forces them together. Triangles have angles summing to more than 180 degrees. Draw a triangle on a globe, from the North Pole to 2 points on the equator. The angles at the equator are both 90 degrees. The angle at the pole adds more. Total exceeds 180 degrees. This represents positive curvature, where space curves back on itself, like the surface of a ball. A universe with positive curvature would be finite in volume, containing only a limited amount of space, bounded but without boundaries, closed but without edges. Finally, imagine walking on a saddle-shaped surface. This represents negative curvature, where parallel lines diverge, and triangles have angles summing to less than 180 degrees. Space curves outward rather than inward, like the surface near a mountain pass or the shape of a Pringle chip. This geometry also allows infinite extent. You can travel forever, never encountering boundaries or returning to your origin. Negative curvature creates infinite space, just like flat geometry, but with different rules governing shapes and angles. Which geometry describes our universe? Measurements point overwhelmingly toward flatness. Multiple independent observations converge on the same answer. Observations of the cosmic microwave background show temperature spots at specific angular sizes, exactly matching predictions for flat space. Studies of galaxy clustering reveal patterns consistent with zero curvature. Measurements of distant supernovae confirm flat geometry. All converge on the same answer. The universe appears flat within measurement. Precision of 0.4%. Space does not curve inward like a sphere, does not curve outward like a saddle. It follows Euclidean rules across cosmic scales. Parallel lines stay parallel forever. Triangle angles sum to exactly 180 degrees. The Pythagorean theorem holds true, but flatness creates a puzzle. For space to be flat, the universe must contain precisely the right amount of matter and energy. Not approximately correct, not close enough, but exactly right. This critical density equals about 6 hydrogen atoms per cubic meter on average. Too much total density and space curves inward, creating positive curvature like the surface of a sphere. Too little and space curves outward, creating negative curvature like a saddle shape. The measured density sits right at the critical value, balanced impossibly precisely. This balance seems too perfect to be coincidental. Early in cosmic history, even tiny deviations from flatness would have grown rapidly. If the universe started slightly curved, expansion would have amplified that curvature dramatically. Imagine starting with density just 1% above critical. By now, space would curve so strongly the universe would have collapsed billions of years ago. Or imagine starting 1% below critical. Space would curve, obviously, today, opening wider and wider. Yet observations show near-perfect flatness after 13.8 billion years of expansion that should amplify any initial deviation. Something must have driven the universe toward this special geometry. Cosmic inflation provides the most popular explanation. This theory proposes the universe underwent a brief period of exponential expansion. During the first fraction of a second, space grew by at least a factor of 10 to the 26th power, an incomprehensible amount. The observable universe expanded from smaller than an atom to larger than a grapefruit in less than a trillionth of a second. This smoothed out any initial curvature. Picture inflating a balloon to enormous size. The surface appears increasingly flat to an observer sitting on it. Curves that were obvious on the small balloon become undetectable on the giant one. Inflate the balloon by a factor of a trillion, and any curvature becomes unmeasurable. Inflate the universe sufficiently, and any curvature becomes undetectable. The observable universe represents a tiny patch of a much larger cosmos, appearing flat for the same reason Earth's surface appears flat from ground level. You cannot see the curvature because you occupy too small a region. Flatness strongly suggests infinite extent. If space has zero curvature and extends forever, in all directions the universe contains infinite volume. Infinite space means infinite matter, infinite galaxies, infinite stars. Everything that can happen does happen somewhere. Every possible arrangement of matter exists. Every variation on cosmic history unfolds in some region. Every configuration, allowed by physics, manifests in some location. Quantum mechanics ensures finite variations in any finite volume, but infinite volume guarantees every variation occurs, not just once, but infinitely many times, repeated across infinite space. Infinity contains everything, but we are living in a special time, a temporary window when the universe reveals itself. Before us, the cosmos was too young, too hot, too simple to produce observers. In the first 380,000 years, matter was ionized plasma. Light could not travel. No eyes could see. No telescopes could function. The universe was opaque, unobservable, hidden behind the plasma curtain. After us, the universe will be too old, too expanded, too isolated for observers to see clearly. The event horizon will have contracted. Most galaxies will have faded beyond detection. Evidence for cosmic expansion will have disappeared. The cosmic microwave background will have redshifted into invisibility. We exist at the moment when cosmic history remains observable, when evidence for the Big Bang still exists, when distant galaxies lie within reach, when the full story can still be reconstructed from available data. This window lasts only a small fraction of cosmic time. The age of observability spans perhaps 100 billion years, from when the universe cooled enough for stars to form, until expansion carries all evidence beyond horizons. Before stars, nothing could observe. After evidence fades, observation becomes incomplete, misleading, unable to reconstruct the full story. The total lifetime of the universe may extend for trillions of years or more. Stars will continue forming for hundreds of billions of years. Red dwarfs will burn for trillions. The universe will exist far longer than the window of observability. We occupy a brief era of cosmic visibility, sandwiched between early simplicity and later isolation. Future observers will inherit a lonelier cosmos. They will see less, know less, understand less, despite potentially superior technology and intelligence. The universe itself will hide its secrets by accelerating expansion beyond detection range, by redshifting evidence into invisibility, by contracting the event horizon until almost nothing remains reachable. The loneliness ahead is not a failure of science, not a limitation of technology, but an inevitable consequence of dark energy. The physics governing cosmic expansion guarantee increasing isolation, and we can do nothing to prevent it. But right now in this cosmic moment, we have the privilege to see. The cosmic microwave background remains detectable. Ancient photons from the edge of the observable universe still arrive, stretched into microwaves, cooled to near absolute zero, but still carrying information about cosmic birth, still revealing the seeds of structure, still showing the baby picture of the universe. 2 trillion galaxies lie within observational range. From nearby spirals we can study in detail, to distant objects showing the early universe, the full range of cosmic structure remains visible, available for study, accessible to observation. Cosmic history can be reconstructed from the Big Bang through cosmic inflation, through the plasma era, through the formation of first stars, the assembly of galaxies, the emergence of cosmic structure. All the major events remain observable, traceable through surviving evidence, recoverable from available data. We are living in the golden age of cosmology. Your cosmic horizon expands by about 1 light year every year. New regions of space become observable as their ancient light completes its journey to Earth. Every second, photons from previously invisible galaxies cross into your cosmic sphere. The particle horizon grows continuously, revealing cosmic territory that was always there, but remained hidden by the finite speed of light. Your observable universe increases in volume with every tick of the clock. The sphere of observability expands, not because new galaxies come into existence, but because light from existing galaxies reaches us for the first time. Ancient photons completing billion-year journeys, bringing images of cosmic dawn. But this growth is deceptive. While the particle horizon expands, showing you more of the ancient universe, the event horizon contracts, cutting you off from more of the present universe. These two boundaries move in opposite directions. You see farther into the past as ancient light arrives from greater distances. Simultaneously, you become disconnected from more of the current universe, as expansion carries present regions beyond reach. The edge moves differently depending on which edge you measure. Consider what this means for cosmic observation. The farthest galaxy visible today emitted its light over 13 billion years ago, when the universe was less than 5% its current age. You see this galaxy as it was in cosmic infancy, young and full of newly formed stars, blazing with blue light, vigorously forming stellar populations. But that galaxy has evolved dramatically since then. It now sits over 46 billion light years away, having been carried by expansion into the distant cosmos. During those 13 billion years of light travel, the galaxy aged, changed, possibly merged with neighbors, exhausted its gas supply, ceased forming stars, evolved into something completely different. You cannot see its current state. The present condition of the galaxy remains hidden beyond your horizon. Every galaxy you observe appears as it was not as it is. The observable universe is not a snapshot of cosmic structure at one moment, but a backward-looking cone through time, showing different epochs at different distances. The farther you look, the farther back in time you see. Look at a galaxy 1 billion light years away, and you see it as it was 1 billion years ago. Look at a galaxy 10 billion light years away, and you see it as it was 10 billion years ago. Each distance corresponds to a look-back time, a glimpse into cosmic history. The observable universe contains all of cosmic history, layered by distance. This temporal structure creates strange possibilities. A galaxy could have already been destroyed by some catastrophic event, a supermassive black hole merger, a nearby gamma ray burst, a collision with another galaxy. But you continue seeing it, because light from before its destruction keeps arriving. The galaxy appears healthy and active in your telescope, but it no longer exists at its current location. You observe ghosts, images of cosmic structures that may have changed dramatically or ceased to exist entirely. The light carries information from the past, not the present. You see history, not current reality. Now, combine this with the moving event horizon. Some galaxies you can see today will cross the event horizon in the future. Light currently arriving from these galaxies will eventually stop. You will watch them freeze at the boundary, fade from view, and disappear. Their final photons will arrive, and no new ones will follow. The connection will sever permanently. Meanwhile, other extremely distant galaxies will enter your particle horizon for the first time. Their ancient light will finally complete its journey, revealing cosmic structures never before observable. Galaxies from even earlier epochs, objects that were always there, but whose light is only now reaching us. Your window into the cosmos shifts constantly. The observable universe changes content over time, not just because galaxies evolve, but because different galaxies enter and exit observability. Some ancient galaxies become visible for the first time as their light reaches us. Some more recent galaxies fade beyond the event horizon and vanish. The inventory of observable cosmic structures is dynamic, changing as horizons move. This creates a cosmic traffic pattern. Galaxies enter your observable sphere from the past as their ancient light arrives. They cross through your observational window. As you watch their evolution unfold, eventually they exit your observable sphere toward the future. As they cross the event horizon and fade from view, the observable universe acts like a moving window, showing different parts of the cosmos at different times. The rate of this traffic depends on cosmic expansion. In a decelerating universe, the event horizon would recede, keeping pace with or outrunning the particle horizon. More galaxies would enter observability than exit. The observable universe would grow in content as well as size. The window would widen continuously, but in an accelerating universe, the event horizon contracts. More galaxies exit observability than enter. The observable universe empties over time. Despite growing in apparent size, the window narrows. The view becomes more restricted. The inventory decreases. We live during the transition between these regimes. For most of cosmic history, expansion was decelerating, as matter's gravity slowed the growth of space. The observable universe steadily accumulated content. More galaxies entered visibility. The window widened. The view improved. But about 5 billion years ago, dark energy began dominating over matter. Expansion started accelerating. The event horizon began contracting. The transition occurred. The window reached maximum width and started closing. We exist during the crossover, when the observable universe reaches maximum content, before beginning its long decline. This moment will not last. Already the event horizon contracts. Already galaxies slip beyond reach. The window narrows with every passing year. Future observers will inherit a shrinking catalog of observable galaxies. They will see the particle horizon expand just as we do, revealing ancient light from increasingly distant regions. But the event horizon will have contracted dramatically, cutting them off from vastly more present cosmic structure. The moving observation window will have shifted to show less variety, less structure, less cosmic richness. The edge moves and the view changes with it. What you can see today differs from what your ancestors could see and from what your descendants will see. You are living in a magical moment when the universe is old enough to understand, but still young enough to see clearly, old enough to have produced observers, but young enough that evidence remains accessible. The balance between these will not last. The window is closing, like catching the most beautiful sunset. Not too early when the sky is still bright, not too late when darkness has already fallen, but right at the moment of peak beauty, when colors blaze across the horizon, when light and darkness balance perfectly. That perfect moment does not last long. You must appreciate it while it exists. And now, as the story ends, close your eyes and be grateful you're living in this special moment. When the cosmos reveals itself, when evidence remains within reach, when understanding is possible, the window will not stay open forever. But right now it is open, and you can see through it, into the depths of space, across the expanse of time, to the very edge of the observable universe.